The third lesson in the unit is on geometric sequences. A geometric sequence is a list of terms with a common multiplication pattern. So remember, an arithmetic sequence was a list of terms with a common addition pattern. So each successive term of the sequence is obtained by multiplying its preceding term by the same number. And this number is called the common ratio. So we learned common difference, we called it a D. Common ratio is an R. And again, given it's the same, if you divided the second term by the first term, or the third term by the second term, or the fourth term by the third term, you will find the common ratio, and they're all equal. Sometimes it's easier to find this common ratio further down the line. So here's 3 quick examples of finding the common ratio. So first of all, I want you to notice that these are not arithmetic sequences, because in example A, to go to 1 to 3, you add 2, but to go to 3 to 9, you add 6. So there's not a common difference. So again, then we would ask ourselves, well, how do you go from here to here? How do you go from here, etc.? And hopefully we see it's a times 3. So the common ratio in this first one is 3. If we look at the second one, first thing you should notice is signs alternate. So when the signs alternate, we're going to have a negative. So to go from -8 to positive, we multiply that negative by a negative, and to go to 4 to -2, a positive times a negative is -2. So then we'd ask ourselves, well, how do we go from here to here, and here to here, and here to here? And remember, it's the second number divided by the first. So however you look at it, we're going to multiply by 1/2. 4 over -8, -2 over 4, or 1 over -2. So again, thinking not of how do I go from one to the other, but actually doing a simple division. And finally, in this last one, how do we go from here to here? Well, it doesn't look that obvious. So if we divided one term by the one before it, so for example, the second by the first, we'd get 0.1, which is equal to also 1 over 10. So there would be our common ratio, 0.1 or 1 over 10. And sometimes it's nice to have a decimal, and sometimes it's nice to have a fraction. So let's go ahead and look at a few examples. The first one, again, is a little bit of algebra. Determine the value of x that would make this sequence geometric. So in figuring geometric, remember it's a multiplication pattern. So 4 to 8, 8 to 16, that's a times 32. So hopefully we would look at this and go, well, that next one has to be 32. So 4 to 8 to 16 to 32 to 64, etc. And then in going ahead and solving it, we would just use that idea of our pattern. So we've already figured out the common ratio. Common ratio is 2. And now we're just going to go ahead and solve that. 3x plus 2 is going to equal 32. And we go ahead and solve that. We subtract 2 from both sides. We get 3x is equal to 30, and we divide both sides by 3, and we get 10. So when x is equal to 10, that term is 32, and it's a common ratio. It's a geometric sequence. This next question is asking us to find the general term. Now we're going to come up with a formula for a general term. I'm going to give you the formula for the general term, but we might actually be able to see it with this simple example. So if my first term is 4, so what I'm going to do is I'm just going to write out the first 3 terms, first 4 terms, And we're going to write it in a creative way. So 8 is equal to 4 times 2. And 16, I know it's equal to 4 times 4, but really it's equal to 4 times 2 times 2 in our pattern. And similar, 32 is 4 times 8, but that's 4 times 2 times 2 times 2 in our pattern. And what we might notice is, wow, we have this pattern here. And if I wanted to go back and do this first one, well, I could write that in the pattern as 4 times 2 to the power 0, because 2 to the power 0 is equal to 1. And what I want you to notice is there is a common idea here. They all have a 4. They all have a base 2. And they have ascending powers. So we're going 0, 1, 2, 3. But this power here is always 1 less than this power here. 1 is 1 less than 2, 2 is 1 less than 3 as well. So if we write our T of, we get T of whatever number is equal to 4 times base 2, that's always the same, and then the exponent is going to be 1 less than our T of. So we could generate a formula based on a pattern in the data, and in this example, that's what it would look like. But there's a common formula for every geometric sequence. And it's T of n. Remember, n is the value of the nth term. The value of the nth term is equal to the value of the first term times the common ratio to n minus 1. So kind of like that thing we have above. If you looked at our numbers above, our first term was 4. Our common ratio was 2, but it really doesn't matter. So that's a really nice formula, and again, I highly recommend you stick that on your formula sheet that you should have been accumulating to make this thing easier. So here's a quick couple of examples of writing the general term of a geometric sequence. So the general term T of n, whatever one I might want to find, is equal to whatever the first term is times the common ratio, which in this case is 4 to the n minus 1. This one here would be T of n is equal to the first term times the common ratio to the n minus 1. So let's go ahead and do a quick couple of examples, because the ideas are quite easy. I'll remind you of a couple of strategies we've looked at over the last couple of lessons, but there's some other little algebra things that pop up. So in this first one, we want to figure out the 9th term. So in this example right here, we want to figure out the 9th term. So here's the information we have. And in this example, it's all written. T of 1 would be 0.5. R would be 4. So that would all be set. But this one, we're just given the 9th term. So this would be 0.5. 4 to the 9 minus 1 is power 8. Now, in this example right here, if you punch this into your calculator would do all the work for you, and that's a good thing. But I just want to remind you about something. If you're doing a question like this by hand, it's really important that you remember order of operations, or BEDMAS. So with order of operations, there's my exponent, and that comes before my multiplication. So in doing this by hand, you'd multiply 4 to the power 8, and you'd get that, whatever that is, and then you'd multiply that answer by 0.5. And when you do that, you get 32,768. So the 9th term in this sequence is 32,768. Well, the question on the right is asking us for T of n. And in this one right here, we don't have the common ratio, and we don't have the first term. But what we do have is we do have the 4th term in the sequence. So here's our T of 4. We don't have the 5th, we don't have the 6th, but we do have the 7th. And again, that's okay. That'll help us find the common ratio, but the common ratio then will help us go back and find T1. So in order to find the common ratio, that's the nice thing about drawing the little picture. We know that to go from here to here to here, I'm going to do a multiplication, and 8 is going to be finished. So in this part of the sequence, 64 is the start, and 8 is the finish. So what we could have is, if I start at 64 and I multiply by r times r times r, which is r cubed, whatever it is, we don't know what it is, the answer will be 8. So here's a nice little equation. And in order to do this equation, we divide both sides by 64, and we get 1 over 8. And again, with our algebra, in order to get rid of a cube, we would do a cubed root. Now, whether you did this in your head or you got out the calculator, the cubed root of 8, or 1 over 8, sorry, is 1/2, or 0.5, however you want to write it. So the common ratio is 1 over 2. Well, that's great because I need that in my general formula. But the question is, well, how do I figure out the first term? Well, again, nice thing is if the sequence is not too long, you can do it by repetitively multiplying or something. So in this one right here, we don't want to go to the right. When we go to the right, we multiply 1 by 1/2. The numbers get smaller. So this would be 32. This would be 16. But what we can do is we can use this pattern and go the opposite direction. So again, this pattern would tell us to go 128. We're doubling going to the left. And then we'd have 256, and then finally we'd have 512. So a pattern, a picture pattern, is a really nice way to see what's happening, especially when you have a small sequence. So there's our first term. T of 1 is equal to 512. So our general term is equal to our first term times the ratio to the n minus 1. And now if we wanted to figure out the 100th term, the 1000th term, we could do it. So a couple ideas there. BEDMAS, we have to be careful about that, especially if we don't have a calculator. And a pictorial pattern approach is a nice way to get a general idea and sometimes the answer. So again, with example number 5, we want to figure out the number of terms. We want to figure out what n is equal to in this one. So here's what we're trying to find the number of terms. And we know T1 is equal to 4. And we know the last term in that string is that. And if we look at the pattern, we know our common ratio is 3. And I guess all we'd have to do is keep on filling in. 36 times 3 is 96, times 3 is, etc., etc. As long as it wasn't too big and we were careful with our multiplication, we could figure it out. But we want to solve this one algebraically. So again, we're going to have our formula, and we're going to plug the right thing in the right place, and here's what we get. And this is a little bit more of a challenging equation maybe for you. You might not have seen it before, but it's doable. So the first thing we're going to do is we're going to get rid of the 4, because we have 4 times something I don't know. So I'm going to divide everything by 4 first. And when I do that, I get 729 is equal to 3 to the n minus 1. Now in doing these examples, especially the ones we're going to do in grade 11, the numbers are not accidental. 729 is equal to 3 to the power 6. So a hint is, if you ever run up against a question and you get to this stage right here, well, you're always going to be able to convert the number on the left to a power, in this case of 3. So if these two things are equal, if this side is equal to this side and the bases are equal to each other, then what has to happen is our exponents are equal to each other. So we don't care about this nasty grade 12 kind of looking equation. As long as we have the general idea of equals means the same, if the bases are the same, then the powers have to be the same. So 6 has to equal n minus 1, therefore n is equal to 7. And if you don't believe me that the answer is 7, just again, fill in those blanks, 36 to 108 to blah, blah, blah. Just figure those things out. And finally, this last one, again, a bit of a practical example that, again, we're only going to 7, so we could solve this pictorially. But the idea is this statement right here. Here's our key thing. The balloon loses 1/10 of its gas every day, every 24 hours. And we have to use that information to identify one of the things we don't know. So let's go ahead and write what we know. Well, a balloon is filled with that amount of gas. So obviously that's our starting point. That's our initial value. And we want to figure out T7. So therefore we know N is 7. And now we just have to figure out the ratio, because this is what I want to know. So I have to know everything else. And the ratio is not 0.1 or 1 over 10. So if it loses 1/10 of its gas every day, just imagine this. On the first day, it's going to have 20,000. And if it loses 1/10, it's going to lose 2,000. It's still going to have 18,000. And remember how we figure out our common ratio? It is the second number divided by the first number. And when you look at 18 over 20, that's 9 over 10, or 0.9. So the common ratio is not 1 over 10, it's in fact 9 over 10. And as soon as we think about that, then T of 7 is going to equal T of 1 times 0.9 to the 7 minus 1, or 6. And again, if you're going to do this by hand, which I hope you don't do, you do the exponent first, then you'd multiply by 20,000. And here's what we would get. So that would be how much gas. So the key thing in this question is determining R, and you might have to write out a little bit of the sequence to figure out what R is.